Hello everyone, I'm Bradley Sward, Assistant Professor of Computer Information Systems at the College of DuPage in Glen Ellen, Illinois. And today's video is going to take a look at converting between binary and decimal using signed representations. So we're going to take a look at binary, which is base 2. We're going to take a look at decimal, which is our normal base 10 system. And we're going to presume that we know that we're dealing with signed numbers. The theme here, the difference between signed numbers and unsigned numbers, is sometimes obvious and sometimes not. In our base 10 system, if I see a negative sign sitting in front of that number, it's very obvious I'm dealing with a negative number. And it's not like, you get away with it. If it was missing, you would say, oh, that's a positive number. So at least in our base 10 system, it's very obvious. But in binary and hexadecimal systems, it's not so obvious. There's no such thing as a negative sign in either one of those two base systems. You have to look at the number in front of you and figure out if it's positive or negative. And you can only do that if you're told or if you know which system you're dealing with. You have to know, oh, this is an unsigned number. Or you have to be told, oh, this is a signed number, to be able to go to look at that most significant bit and know if I'm supposed to go down the route that we're going to show you to how to handle a negative number or how to flip it to turn it into a negative number into positive. For these examples in this slide, we are going to presume we're living in a signed universe here. So we know that up front. So those three numbers that are in the green figures, how do we know? So the top one, 111101110. All I care about is that first most significant bit. It's a 1. That's screaming out, I'm a negative number, and we don't know how to do that just yet. We haven't shown how to do it, but we have to do something if we wanted to convert that or take a look at that and go, oh, what value is that actually in something I can read? So the second example, 00001010, that most significant bit is a 0, and you see that there's padding. I'm also going to have to tell you with these kind of signed numbers how many bits of storage we're dealing with, because without those front-facing zeros, if all I gave you was 1010 and following the rules I just told you, there's always going to be a 1 to start the number. So you go, that's a negative number, but that's not true. It's obviously a positive number, so I have to pad out 8 bits of storage with the zeros so that I know that most significant bit is a 0. And then to finish up down below at the bottom here, if all 8 bits of these things are 1s, there we go, if I'm dealing with an unsigned number, like we've done in previous lectures, I know from that if I add it all up, I'm dealing with positive 255. However, looking at this, if I go, that's a negative number because it's signed, you go, what number is that? And we'll show you in a little bit here that that number comes out to be -1. So you either get a very large positive number or a very close to 0 negative one. So this example also shows I'm dealing with a signed number, and I'm looking at this number. I want to convert it from our binary base 2 into my base 10. I want to look at that and go, what number is that? And of course the number is 44, but how do we get that? And the first item of business is to look at the most significant bit. That's going to be pretty much the theme of this entire lecture and the next one when it comes with converting binary to hex. But looking at that, I see a 0, and I go, that's a positive number. So you know how to do this already if you've already seen the previous videos. You do the exact same work as before. There's nothing to do. We don't worry about anything else. You've got it down. You just add up the bits that are 1, and you add up the powers of 2 to get your solution. So 00101100, that comes out to 2 squared plus 2 cubed plus 2 to the 5th, or 32 plus 8 plus 4, sums up to positive 44. And the next slide will show what to do when you're dealing with a negative number, and that changes everything here. We need to introduce a brand new algorithm in order to understand positive numbers and negative numbers and what we call the additive inverses. So this slide is pretty good at showing that. So there's something called 2's complement. You're going to see this anytime we need to deal with basically figuring out I'm staring at a negative number in either binary or hex, and I got to convert it into decimal. You're going to be doing this 2's complement so that you can turn that negative number positive so you can do the math the way that you're used to doing it. So the principle works as such. Say I take any positive number x, positive number, and I say I want to add it to its additive inverse, and I mean by additive inverse just basically negative x. So basically just look at the number line, pick a number on the positive side, x, pick a number on the exact opposite side, negative x, add them together, and you will always get 0. It shouldn't even matter what base system you use, because it should apply in base 2, base 6, base 10, base 22, base 1 million. If I take a number and I add its additive inverse, the number on the opposite side of the number line, doesn't matter how I represent it, the result should always be 0. So in these two cases on the left-hand side of the slide, 5 plus negative 5 gets me 0. And in this case, all that addition, 0, 0, 0, 0, 101 plus 1, 1, 1, 1, 1, 0, 1, 1, does get me 0. And we do have to eliminate that extra carry bit to make it work. But it does happen, and we'll discuss that in a future slide as well, or maybe this slide when I'm discussing how this algorithm works. In this first example, I'm taking positive 1, which in an 8-bit manner here. So I'm taking 0, 0, 0, 0, 0, 0, 0, 1, and I'm going to say, what is the additive inverse, or what, basically trying to figure out, get me negative 1 from positive 1. So here is the algorithm. We haven't described it yet. It's very simple, and it always works the same whether I'm going from negative to positive or positive to negative, always the same. So take my starting value, my 1, and then all you do is you take all of the bits inside of there and you flip them. You basically do the NOT operation on them. All the zeros become 1s, all the 1s become 0s, so that becomes 1, 1, 1, 1, 1, 1, 1, 0. And now I take that result and I just add 1 to it. And then my end result of all of that is 1, 1, 1, 1, 1, 1, 1, 1. So you're like, do I have the correct answer? Sanity checking this thing is always important. So what you can do is if I take positive 1, which is exactly what you see here, and I take negative 1, which is the 1, 1, 1, 1, 1, 1, 1, 1 we just generated, if we add them together, just like we see there, plus 1 plus negative 1 gets me 0, I better get 0 when I add that all together in a binary fashion. And like we were discussing, it does add up to 0, but you're like, well, what about that extra 1? But as we will see when we discuss stuff more in assembly language, that carry bit gets lost. It works perfectly if you just forget about that carry bit. Only the 8 bits that we're dealing with here, they're all zeros. They're all we care about, and it works. So here is an example that's a little more close to what you would see in normal use in the real world. So I'm given a number, 111111011, and I go, what is that in decimal? And then I'm told, oh, it's a signed number. So again, it could be a completely different number if this was an unsigned number, but we know it's signed. So how do we deal with this? So I look at the most significant bit of this, and I go, it's a 1, so I know I'm dealing with a negative number, so I have to do this 2's complement deal in order to kind of work it down. Unless I know some other fancy math, and actually I can actually look at that and go, oh, that's negative 5 just by doing a couple tricks, magic, right? But I'm not going to describe it just here. If you want to, I can always send me an email. I can always describe to you how another alternate way of solving this problem. But anyway, coming back. So I'm taking that number, and I'm like, I know it's a negative number, so I got to slap a negative at the end. That's always a hard part. It is hard to remember after you do all this math. You got to slap a negative, because sometimes you'd be like, you forget it, and it's almost like that plus C if you've ever dealt with calculus. In integrals, integration, if you forget that plus C, you lose points because essentially you didn't finish the integral, or you absolutely didn't do the math right, because you're telling me a number that's completely opposite on the number line. So coming back, okay, take my number, flip all the bits, so it becomes 0, 0, 0, 0, 0, 1, 0, 0, add 1 to that, and you get 0, 0, 0, 0, 0, 1, 0, 1, which from previous lectures at this point we know that resolves down to a 5. That's a positive 5 listed as the result of my 2's complement math. And again, I know that's correct, so if I take my starting value and I add that result, I get all zeros from the result of that operation with the carry bit, which I don't care about, which is really cool. So now I know that that result is a positive 5, so I just take that positive 5, slap the negative on it, and I know at the end of all of this, my 111111011 is negative 5 in decimal form. So now it's your turn. We'll just do the same thing for a different number. So I'd like you to try to take 1101 1010, and I'll tell you up front it's a signed binary value, and I want you to figure out what number that is in base 10 decimal. So I'm looking at the first most significant bit of this value, and I know it's a signed value, and I see that it's a 1. so I know it's a negative number. So I know I have to apply the 2's complement to this number to be able to figure out what the positive value is so that I can just slap a negative on at the end. So just like the previous example, I take my starting value, which is the number given, I flip all the bits, so that becomes 0, 0, 1, 0, 0, 1, 0, 1. I add 1 to this, which gets me to my final result of 0, 0, 1, 0, 0, 1, 1, 0. So then, sanity checking that thing, because it's very easy to miss a 1 or a 0, I take my starting value, I add my result, I get 0 with the 1 for the carry bit, which gets lost to time, so my result is 0, so I know I'm good. So I know at least I have the correct binary representation of the positive value. Now I just have to take that positive value in binary and convert that into decimal, and that's as easy as anything we've ever done before. You're just taking the 1 bits, adding up the powers, and go. So that is 2 to the 5th power, or 32, plus 2 squared, which is 4, which gets me 36, plus 2 to the 1st power is 2, 36 plus 2. So that is a positive 38 sitting in front of me. So all I remember, I got to throw that negative sign in front of this thing. So my 1101, 1010 value that I'm starting with in signed decimal form, it's the same as negative 38.